Ladies and gentlemen, welcome to the Law of Conservation of Mass, which is also part of Lesson 13. We are going to get started talking about what do we mean by conservation of mass. So we already discussed that a chemical reaction conserves energy. So the conservation of energy, meaning energy cannot be created nor destroyed, just transferred. During a chemical reaction, we said that the atoms of a chemical reaction are the same on both sides. So whatever the reactants are, they'll show up in the products. They just may look a little bit different. Okay. That is what we are talking about with conservation of mass. The total mass of our reactants will equal the total mass of our products. They just may look different. In a perfect world, in the closed systems that we have, closed systems meaning energy and matter cannot escape. Okay. Think of like a test tube with a stopper on it. Okay. I wonder if I can pull this away. No. That's an example of when you would have a closed system. An open system is when you exchange between the surroundings, which is more what we do an open beaker. Okay. What we're trying to say though is that the conservation of mass will always be observed in closed systems. Okay. So in a perfect system where it's closed off, we put a stopper on the top of a beaker, we should be able to see the mass that goes in is the mass that comes out. Now, the reason why in an open system, one that can exchange with the atmosphere doesn't work that way is because sometimes gases or substances that can be evaporated go off into the surroundings. Well, if that happens, then all of a sudden we don't have the mass that goes in being the mass that comes out because we lost mass due to the escaped gases. So when we talk about conservation of mass, we're talking mostly if we're saying closed system that they should be equal. If we're talking open system, they're going to be a little bit different. So in a chemical reaction, the conservation of mass must be shown by using coefficients. This is the start to the idea of balancing. So what we have here is we have a system in which two hydrogen atoms and two oxygen atoms are going to become H2O. Okay, so hydrogen, oxygen to water. What we want to do is we want to make sure that we conserve all of the atoms that are in this reaction and make sure that they work together to have the same amount of mass. So here, if I have two hydrogen atoms here, I should have two hydrogen atoms here. That's perfect. I see that. If I have two oxygen atoms here, that's what this 2 means, I should have two oxygen atoms here. Well, that is not the case. So what we would do is we would say we have 2 here, but 1 here. So what we're going to do is we're going to try and fix this so that they are equal. In order to do that, what I want to do is I'm going to put a 2 in the front of here. And what that does is it changes how much hydrogen I have. 2 times 2 is now 4. So now my products have 4 hydrogens. I want to conserve mass. So that means I have to make sure that if I change hydrogen on this side, I change it on the other side. So I'm going to add a 2 here. And now I have 4 on this side. So these are equal. I still have 2 oxygens here. This 2 now tells me I have 2 oxygens, so I have 2 oxygens as well. So now they're equal all the way across. But I've also gone and balanced my chemical equation. I've said I have 4 hydrogens, 2 oxygens, 2 oxygens. So what I want to do is we want to make sure that we can do it again in this way. Oh my goodness, you guys, something's going on here. Keep clicking and things are not working. All right, there we go. So let's erase these and try it again. Okay. So let's talk about the reactions in this case. Okay. So here we have the reaction of methane gas with oxygen, creating carbon dioxide and water. This is called a combustion reaction. We're going to learn about those. But again, we want to start by figuring out, do we have the same amount all the way across? I'm going to start with carbon because it's right here. I have 1 carbon here and 1 carbon here. So 1 and 1. Perfect. I'm now going to look at my oxygens to see if my hydrogens to see how that's going. So I have 4 hydrogens here because H4. And I only have 2 here. So I'm going to remind myself I have 4 and I have 2. And how many oxygens do I have? I have 2 on my reaction side, and I have 2 on this side, but I have 1 more on this side, so I have 3. All right. So this is not balanced at all. This is not showing conservation of mass. So what I'm going to do is I'm going to say my carbons are fine. I want to fix my hydrogens first. Okay. So I'm going to go over here to the reaction side, the product side, sorry, and I'm going to add a 2 here to make this 4. So now I have 4 and 4. By doing that, however, I went from having 3 oxygens on this side to now having 4 oxygens on this side. Because if I count it, 2 here and 2 here. So that's 4. The nice thing about that is it makes my life a little bit easier on the reactant side because now I want 4 on this side. I just put a 2 right here. Sorry for that one. And now I'm balanced. I have 1 carbon on each side. I have 4 hydrogens on each side, and I have 4 oxygens on each side. So that is the idea of conservation. What goes in on one side has to come out on the other. Now, the thing is we show this in the process of balancing. So we balance chemical equations to help us understand how to keep products and reactants the same. So in balancing chemical equations, we always want to do big atoms first. So essentially, guys, anything that isn't hydrogen or oxygen. So start with the big things, carbons, nitrogens, fluorines, bromines, whatever. Then we want to balance our hydrogen atoms. Then we want to balance our oxygen. So these are the rules you are going to follow as we go through and try and balance chemical equations. So this is underneath lesson 14. So let's talk about this one. Let's try and balance this one. In this case, ladies and gentlemen, we're going to get into a special rule that I'll talk about here in a second. So let's start the same process we've been doing the whole time, balancing it out. So everything except hydrogen and oxygen. So iron first. So I have 1 on this side and I have 2 on this side. This is iron. Fe. All right. I now want to balance my oxygens. I have 2 on this side and 3 on this side. Okay. Let's go through and let's fix this up. So I want 2 hydrogens on 2 irons, sorry, on my reactant side. So I'm going to put a 2 here. I've now balanced these out quite nicely. Okay, 2. But my problem then ends up right here. I didn't balance out my oxygens, and I can't balance out my oxygens because I can't put anything in front of here to randomly change it because then it would change iron. So this is a special rule that we're going to talk about called the odd even rule. This means there is an odd number of atoms on one side, so 3 would be odd, and an even number of atoms on the other side. This is the even number. So what that means is, so what we want to do is we want to do what we call the odd even rule. As I said, we are going to stop, erase what we already did, and double it. So we're going to go back to my pen, make sure we have it. So instead of 2, we're going to put 4 here. So I'm going to erase this 2, and I'm going to add it as a 4. Okay. Well, this changes the whole story because now this side isn't even. So I'm going to add a 2 here to ensure that I have 4 irons, like that. Well, if I added a 2 here, that automatically means this 2 is also multiplied to this 3. So instead of having 3 oxygens on this side, I now have 6. Well, this is nice because now these are both even numbers on either side of the equation. So I'm going to add a 3 over here to balance this out. And that is the odd even rule, where you try it. If you have an odd number on one side and an even number on the other side, erase it, double it, and try again. All right. So balancing. Hopefully it's starting to make a little bit of sense in how you can balance chemical equations. We're going to do a few more quick examples, and then I will let you try it out yourself. So here is another one that you can try, you can write down, and we can balance out together, okay? This is tin oxide plus hydrogen gives me tin plus water, okay? So again, we're gonna take our pen, we're gonna add in our stuff, so tin, hydrogen, and I'm gonna do it in the order that my notes told me. Biggest atoms first, then hydrogen, then oxygen. So on this side I have 1, and on this side I have 1. So there's 1 and 1. On this side I have 2, on this side I have 2, so I'm gonna go 2, and 2. So far I'm looking pretty good. On this side, I have 2 oxygens. And on the other side, though, I only have 1. So again, we go back into our stuff and we fix the side that doesn't have enough. I want 2 on this side, so I'm going to put a 2 here. Because I changed the products of hydrogen, I now made hydrogen's products a 4. I need to go back and fix over here. And then I need to check it. I have 1 tin, 1 tin. Okay? 2 oxygen, 2 oxygen, 4 hydrogen, 4 hydrogen. And that is now balanced. So we have balanced all of those. And we have figured out how to make sure that we have conservation of mass. Remember, conservation of mass means whatever goes in has to come out. So we have to balance, so we have the same amount of atoms on one side of the reaction as we do on the other. So odd even rule, which I've already stated. Odd even rule means that if you have an odd number on one side and an even number on the other side of the atoms, you need to stop, erase, and double, okay? Now, the other thing is if you have polyatomic ions such as NO3, PO4, SO2, SO4, SO3, those kinds of things, you have to keep them together. So in this example down here, NO3 is right here, but is also right here. Keep it together, balance it as a unit. So let's just go through and just balance this one really quickly. Starting with everything except for hydrogen and oxygen. I have 2 carbons here, so I'm going to add 2 carbons here. Okay, works out. I now want to go back and check my hydrogens. I have 6 hydrogens here and only 2 here. So I'm going to put a 3 here. Okay, that gives me 6 hydrogens. I now have 2 times 2 is 4. So I have 4 oxygens here and I have 3 oxygens here for a total of 7. Okay. Over here, I only have 2. So this is a problem. This is an example of the odd even rule. I have 7 on one side, 2 on the other. So I have to go back, erase my original work, and double it. Okay, so I'm going to go back. I'm going to use a different color. I'm going to put a 6 here because I had 3. And I'm going to put an 8 here because I had 4. Oh, I had 2. Sorry, I had a 2 there. What was I doing here, guys? That's a 4 now. Let's try that again. There we go. Sorry. Okay, so I have 4 and I have 6. So let's go back and double check. I now have 4 carbons, so I'm going to put a 2 here. I now have 4 carbons. I have 12 hydrogens. Oh, perfect. I have 12 hydrogens. I now have 8 plus 6. So this is now 8. And this is 6. That makes it 14 oxygens. I have 2, so they're both even numbers. So I'm going to use 7 here to make up for that 14. So that's the odd even rule again as a quick show. Down here for polyatomics, we want to balance them together. So I'm going to start with my calciums. They're balanced. I'm going to go to my aluminums. They're balanced. I'm going to go to my chlorides. 3 here, 2 there. And I can't balance that because they're odd even. Let's look at NO3. Oh, they're odd even as well. So I said this was balanced and this was balanced. Okay. And this was balanced and this was balanced. So CAs and ALs. So what I'm going to do is I'm going to go back. And so since they were both 1, I'm going to now make them 2s. Okay. And let's see if this helps my stuff. So I have 2 calciums here. I'm going to add a 2 here. Okay. I have 2 aluminums here. I'm going to add 2 here. So let's just double check to see if everything's in balance and fix what we need to. So I have 2 calciums, 2 calciums, 2 aluminums, 2 aluminums. I have 6 nitrates. I only have 4 nitrates, so we're going to have to figure that one out. I have 6 6 chlorides and 4 chlorides. So I have to go back and try again, and I'm going to have to erase and double it, okay? But again, making sure that I am balancing and keeping them in check. So what I can do is I can go and I can take my eraser here, erase this, and try again. So I'm going to balance, this one will be a 4, And I think this one will be a, okay, so 4, 4. Let's do chlorides now. 8. Can we get 8 out of this? No. So we go back and double. This one's going to take us a long time. I'm not going to go do it over and over again. Okay. So that's okay. But there's one other rule that you need to write down that I haven't had a chance to talk to you a ton about, and that's if a reaction has water on one side of it and OH on the other, so a hydroxide, you need to change your water to a OH. So what I'm going to do is I'm going to show you guys an example of that somewhere. There we go. So what you have here is the reaction calcium hydroxide, okay? And that would be phosphoric acid becomes calcium phosphate and water. Okay, but if you notice, I have a hydroxide right here, and I have a water on this side. So what I'm going to do is I'm actually going to cross off that water, and I'm going to change it into an HOH, which essentially is 2 hydrogens and 1 oxygen, just written better so you can see the hydroxide. Now I want to balance it because now I have OHs here and hydrogen here. It makes way more sense to balance because it's easier to see. So I'm going to start with my calciums and see if they're balanced. So I have calcium here with 3 here. So I'm going to add a 3 right here to help with the balancing. So now I have 3 calciums, 3 calciums. I'm going to look here and I'm going to go with, I have 6 hydroxides. So I'm going to add a 6 here, okay, to help balance out my hydroxides. All right. So I have 6 hydroxides. So let's go back. Let's check my PO4s. I have 1 PO4 here, but 2 here. So I'm going to add a 2 in front here, just to make sure that I balanced off my phosphates. And then let's check my hydrogens, which is last. I have 6 hydrogens and 6 hydrogens. So I am balanced, 3, 2, 1, 6. Okay. Again, balancing hydroxides and hydrogens separate if you have water on one side, but OH on the other. All right. Last one. The last one we're going to balance is right here. And this is, again, an example of polyatomics. But this time, again, the polyatomic is in the front. So be careful. This 4 right here is attached to the hydrogen. But this is an ammonia polyatomic. So keep it together when balancing. See how it shows up here on one side and here on the other? It's together. Okay, so let's start with anything other than hydrogen and oxygen. So iron, iron, balanced. Great. Nitrate, nitrate, balanced, great. Chlorine, chlorine, not balanced. So I'm going to add a 3 here. I'm going to stop because that changes my overall amount of ammoniums on this side. So I have 3 ammoniums on this side, so I'm going to change it to 3 on this side to ensure that I've balanced off that entire polyatomic. So I now have 3 ammonias, 3 ammonias, 3 hydroxides, 3 hydroxides. So I am fully balanced. All right, and that is how you balance that equation. So ladies and gentlemen, sorry for the few interruptions here or there. If you have any questions or you have any concerns, please let me know.